Okay, for the next part, you're going to have students do 13, 14, and 15. So in 13, it's having them look at something sort of similar to this. That there's a carrying capacity in the environment, that the population goes up. Now in the case of their flies, it then crashes at the end. But then they're going to calculate this room to grow statistic, okay? And so it asks them in A, it says, for example, if a population size is 75 and the carrying capacity is 100, how much room to grow does it have? So if it's at 75% of the 100, it's going to have 25 to grow. And then it says to write B, to write it as a percentage. So if your carrying capacity is 100 and you have 75 left to grow, then you've got, or you're at 75, then you have 25% left to grow. So how did you figure out 25%? Well, you divided this by the carrying capacity, right? And that gave you 25%. So that's the first one. And then it says, what if we have a population where the carrying capacity is 600 and we are at 250? So if you wanted to figure that one out, you would simply do that and figure out how much room to grow it has. And so if we write a generic for that and we call the carrying capacity K, then you're taking the carrying capacity and you're subtracting the number of the population right now and you're dividing by the carrying capacity. All right? And that gives you sort of a modification to your population growth equation. All right? And so how do we want that to modify the growth equation? And they're going to figure this out first and then you're going to discuss it. Oh, actually, let's do 14 first. So on 14, it asks them to record the 4 different carrying capacities for their 4 different jars. So that's what they got from their graph that they drew before. What was the approximate carrying capacity? And it asks them, should they be different? Can you hypothesize reasons? Anything is right here. So if they think, well, obviously the smaller jar is going to have a lower carrying capacity, but as far as vestigial flies versus normal flies, I don't know, maybe the vestigial flies can't climb out of the waste material very quickly because they can't fly, and so their carrying capacity is lower because they get stuck down in the muck. Or maybe the flying ones need more space in order to mate or whatever, and so in a flying population, the carrying capacity might be lower. They can come up with all different hypotheses, but the point is they want to be thinking about what things might cause differences in the carrying capacity between the different populations. So then 15 asks, how can we factor this part of the equation into our original equation? So if you remember, the original equation, in order to figure out how many babies, so the change in the population over time, which remember is always how many babies? How many babies? What we did to figure that out is we took our R, our rate at which it's growing, and we multiplied it by n. And then we just add it to the original population. But in this case, if you're down here in your population, do you want to be growing at your full potential? Well, yeah, you're right down here. So we want to be growing at like 100% of our R. Let's say we're at 50% of our carrying capacity. How much do we want to be growing? Well, we want to be growing at 50% of our R, right? If we're up here at 90% of our population, how much of our R do we want to be growing at? 100%, 50%? If we're at 90% of our population growth, we only want to be growing at 10% of our R. Does that make sense? Because we want it to slow down when it reaches the carrying capacity. So this tells us at what percent left do we have? It's the 25% or the 10%. So if we always took, in order to find out the number of babies, if we always took our R and first multiplied it by our room to grow, so that we get like 10% or 50% or 100%, right? If we multiply it, so we take k minus n over k, and we multiply that by the R first, and then whatever that new R is, we multiply that by n, right? Then, as we get larger in populations, our R gets smaller, and we grow at a slower rate. So eventually, we totally slow down and we stop at the carrying capacity, okay? So this is called logistic growth. All right? And that's the logistic growth equation. Now, this is a derivative. The e to the rt, so if you have mathematicians in there, like they're going to want to say n e to the rt. Yes, that is the equation if you want to do fancy calculus, but we're going to use this because it's much easier to think about. The number of babies is the room to grow times R, then multiply that by n. That's the number of babies. Then you'll add that to the population that was already there and get the new population. So they're going to figure this out at number 15. You're going to walk around and help, and then have them draw it on their boards, and then have a discussion about it. So then 16 through 17 is going to ask them to use that equation to predict what the expected numbers should be if the population was growing logistically. All right, so I'm going to do just one calculation right here so you can see how to use it. So let's say we started with, let's say we have a carrying capacity of 100, and we're growing at a rate of 2.0 for whatever hypothetical population we have, okay? And we're starting with 10 individuals, all right? So let's say we have that hypothetical population. Then what you're going to say is, all right, if I want to know how many babies these 10 individuals are going to have under this model, then we're going to say, all right, I'm going to do my k minus n over k. How much room to grow do we have? So we're at 90% of our R. Okay, so we're going to take that 90% and we're going to multiply it by 2.0. And then we're going to multiply it by our 10. Okay, so if I do the math, so we're taking 90%, 0.9 times 2. So we're not growing at 2, we're growing at 1.8 because we're already a little bit of the way up the curve. 1.8 times 10 gives us 18. So our next population size, n, this was n0, n1 is going to be 18. Okay, or I'm sorry, 18 babies, sorry. So that gives you 18. If we do 0.9 times 2 times 10, it gives us 18 babies. So what is our N2? We have 18 babies, we started with 10 individuals, so our next generation, or N1, sorry, our N1 is 28 individuals. Okay? Let's do another one. So then we take 28. If we're at 28 of our carrying capacity, so 100 minus 28, what percentage of our carrying capacity is that? Okay, we multiply that by 0.20, or 2.0, and then we multiply that by the 28 individuals we have. How many babies are we going to get out of that? All right, so let me do that one. We have 100 times 2. So now we're growing at a rate of 1.44. So this times that is 1.44 times 28 individuals gives me approximately 40 babies. We add that to our 28 individuals we had, and our next population, N2, okay, is 68 individuals. And you keep going all the way down, and they're going to use whatever their JAR's R was from the 4th generation, and they're going to calculate this all the way down to 10, okay? And then they're going to see if that better matches the curve that they actually saw, and it should better match until the end when it crashes. But it should better match, okay? If it doesn't match, this is a good time to have a discussion. Why didn't your numbers match what you saw? And the chances are that generation 4 was not a good indication of the growth rate. So they could try a different generation, see if they get a better growth rate, and then use that number. Or generation 10. I mean, we don't know because the growth rates will vary, right? Depending on the generation. Okay, and then number 17 says, when populations are growing in a limited environment, when is their growth the largest? When are they adding the most number of babies? Is it down here? Well, no, it's not down here because down here they have very few individuals. They're having very few babies. Is it up here? Well, no, up here we have a ton of individuals, but they're having very few babies. So the maximum growth of a population, doing logistic, is right here at 50%. And if they actually graph it, they could see it. If they looked at number of babies added over time, right, then they would see something like this. So at 1/2 the carrying capacity, you're going to have the most babies added, the most bang for your buck at right here, at that turning point. Okay? Okay, and then I'm going to stop it and then do the last part.